We're going to go ahead and get started now. I'm next session chair, Leslie Looney from Illinois, and the first talk we have is Elijah Bernstein-Cooper talking about H1 to H2 transition in subparsec scales.
All right, thank you for the introduction. My name is Elijah Bernstein-Cooper. I'm a graduate student here at University of Wisconsin-Madison, and today I'll talk to you about an observational study of the H1 to H2 transition on subparsec scales. I'd like to thank a few folks in the crowd who have been instrumental in this work: Snezhina Stanimirovic, Minyoung Lee, and Brian Babler. Okay. So previous extragalactic observations have found a saturation in H1 surface density on kiloparsec scales. So this is plot of star formation rate against H1 surface density from Begal 2008. And for a variety of star formation rates, we never see H1 surface density going past about 10 solar masses per parsec squared. Now this saturation in H1 surface density has also been seen in local clouds. This is a H1 column density map from Lee et al. 2012, who found a similar H1 surface density saturation on subparsec scales. Now this observational trait can be described by molecular hydrogen formation. And previous recent models of steady-state H2 formation have been able to describe this H1 surface density saturation as a threshold in atomic gas. So just to give you an overview of the model developed by Krumholtz and Christopher McKee in the room, we have a molecular core which is surrounded by a cold neutral medium atomic envelope and a warm neutral medium envelope. And the amount of molecular hydrogen is balanced between formation of molecular hydrogen on dust grains and destruction by an incident interstellar radiation field. So the molecular hydrogen in the core is shielded by dust, which is associated with the cold neutral medium envelope in this model. And once there's enough dust shielding of the interstellar radiation field, H2 will begin forming and begin self-shielding. This is a runaway process. So once H2 begins forming, the core will become entirely molecular. Or the transition is very sharp between dust shielding and H2 self-shielding. Okay? So two conclusions from this steady-state model is that the shielding dust is associated with the cold neutral medium atomic envelope, and that dust shielding is equally important as H2 self-shielding in the formation of molecular hydrogen. So observationally, this model predicts for an H1 surface density as a function of a total gas surface density that there will be a linear rise in H1 surface density as while dust is shielding, or before molecular hydrogen begins forming. However, once molecular hydrogen begins forming and H2 self-shielding begins, all additional atomic gas is converted into molecular gas, thus predicting this H1 saturation or threshold as identified in the model. So because dust is associated with the cold neutral medium and varying densities, and the cold neutral medium has varying densities, this threshold for solar metallicity will be between 3 and 20 solar masses per parsec squared. And for varying metallicities, the dust will have different effectiveness, shielding effectiveness, and so this threshold will also depend on the metallicity of the dust. All right, so we would like to test this model prediction observationally, and we're going to do this on subparsec scales. We're going to measure H1 surface density with H1 spectral observations and total gas surface density with optical extinction using a dust-to-gas ratio. All right, we adopt the GALFA-H1 observations and, well, little formatting issue, and Planck AV optical extinction observations, which were derived from fitting large-grain dust spectra. And we derive dust-to-gas ratios and determine the total gas surface density. So here is a map of the Planck optical extinction of the Perseus and California and Taurus molecular clouds. So we are extending Li et al. 2012 sample from the Perseus cloud to California and Taurus. And this sample of giant molecular clouds will allow us to test these models in different environments. For instance, California has 5 times the mass of Perseus, yet half the star formation rate. Okay. So to test this steady state model, we need to identify regions where all the molecular cores have similar shielding envelopes. And this is predicted to be on region scales of about tens of parsecs. So here is an example region in the California molecular cloud. And we're going to examine the H1 surface density as a function of the total mass surface density. And this is a 2D histogram of our observations. And we see this saturation at about 11 solar masses per parsec squared. Now let's examine this. Now let's take a look at this saturation for many other core regions in these giant molecular clouds. So we'll extend our sample to about 30 core regions, exactly 30 core regions, and examine the H1 surface density threshold. So this is a Planck contour map overlaid, a Planck AV contour map overlaid with the H1 surface density threshold identified in each core region. And we can see that there is a pretty narrow range of H1 surface density thresholds, all within the predicted range of thresholds from this steady state H2 formation model. Right, so we see the surface density threshold varying by only a factor of 3 across these giant molecular clouds, all with varying environments. All right. Now let's apply the model to our observations. We fit the model prediction of H1 surface density as a function of total gas surface density. And we would like to understand perhaps the importance of dust shielding in these core regions. Right? So say we have a larger radiation field. We will need more dust to protect the molecular core in order to begin forming H2. And so dust shielding will be dominant over H2 self-shielding in this case of a large radiation field. And the inverse is true for a smaller radiation field. We need less dust before H2 begins self-shielding. All right. So now let's plot the dust versus H2 self-shielding ratio on the same optical extinction map. And we can see that in every core region, the dust is accounting for more of the shielding of these molecular cores in each of our core regions. Okay. Now we would also like to test if the model is consistent with observations, not just if it can fit our observed H1 and total gas surface densities. So because dust is associated with the cold neutral medium, the density of the cold neutral medium will trace the amount of dust and thus the amount of shielding. And so the models predict the number density of the cold neutral medium shielding envelope, or of the atomic envelope. And we can compare these predicted number densities of the atomic envelope around these molecular cores with by converting spin temperature measurements of cold components in the region. So this is a map from Steinimowicz 2014. And the red crosses represent the absorption sight lines in this survey. And I have used a sample of cold components within this region and assumed a pressure equilibrium between the atomic gas phases and used the spin temperatures derived in this survey to convert to a neutral gas density. So now we have a predicted and observed neutral gas density distribution. So let's compare the cumulative distributions of the neutral gas densities. And we see that the observed neutral gas densities within the region surrounding these three molecular clouds is much broader and higher. So the predicted number densities of the atomic shielding envelopes around these molecular cores are more diffuse. So after applying the steady state molecular hydrogen formation model, we have found that the shielding dust is associated with multiple atomic phases because we are observing the model is predicting a more diffuse atomic envelope. We're unsure if this is CNM plus WNM or some unstable neutral medium. But that'll be left for future observations. And we've also found that dust shielding is more dominant in these molecular cores than H2 self-shielding. Okay. So just to recap, we found a nearly constant H1 surface density across these three molecular clouds, all with varying star formation rates and masses. And after applying a steady state H2 formation model, the model is predicting that dust shielding is dominant in these molecular cores, and that the shielding dust associated with the atomic envelopes, the atomic envelopes associated with the shielding dust are in multiple phases. The atomic envelopes are diffuse. All right, so thank you, and I'll take any questions.
In the back first, Adam.
Can I just yell?
She's almost there.
Subparsec is good. Have you played with the resolution to see to what degree? I mean, if things are highly clumpy, then the universal surface density scatters, right, and becomes a function of resolution. Have you played with making things worse or better?
We have not played with any better resolution. Oh, yes.
You need a microphone. Sorry.
So we did make a comparison between LabH1 data and the GALFA-H1 data. There is a factor of 10 difference in terms of the resolution. The results are really similar. I think the reason is mainly the H1 is dominated by the warm gas, which is diffuse, filling most of the volume. Yeah.
And we've seen a similar saturation H1 surface density in extragalactic observations as well, which are on much larger scales.
Other questions?
So I think you also need to know something about the ambient flux in UV. What did you assume throughout the region? The same number, and what was it?
For a given molecular cloud, we derived the radiation field from a median dust temperature derived from the Planck maps.
Does that vary a lot from one piece of your model, one piece of your data to another?
So the inner regions of the molecular clouds do have very low dust temperatures, suggesting that the radiation field has been attenuated quite significantly. However, the steady-state models adopt the ambient radiation field incident on a molecular cloud. So, the regions that we use to derive these radiation fields are quite large. So they include the diffuse dust.
So it's basically a G01 that you're using, right? General ambient interstellar radiation field.
Yeah, the derived radiation fields are all around 1 Having field.
Okay, we have time for quick DG questions. Oh, okay, great. Okay, great. Let's thank Elijah.